students. Today we'll see the interesting topic input coupling capacitor. So what I am going to derive and study is what is the cutoff frequency, at which point the gain is going to be a saturate. If it is less than your cutoff frequency, what is the limitation, what is the formula while you are considering the input coupling capacitor. That is your objective. Before you start, let me start with the basic so that you will be very clear, right? So you can see here like the interesting part you can see in this graph. This is a frequency and this is your amplifier. So you can see you have done in lab, right? You are increasing the function generator from the 1 hertz to, in terms of megahertz, you are increasing. In the lower frequency the gain is less. You have a rollover. There is a roll off function you have. That means gain will be keep on rising, but here you can see that it is a limitation in your gain. So that is very important to understand. So here there is a roll off function. That is a limitation in the gain because of the reactance. Because of the which reactance you want to understand. Because of this reactance. Okay students, because of this external capacitor, because of the coupling and the bypass capacitor. This will be considered in the low frequency equivalent circuit model, and correspondingly the stay capacitance and load capacitance will be acting as an open circuit. That is the interesting part. So that will be act as an open circuit. That will not be considered in the equivalent model. It will not work mathematically. So the limitation of gain in the input side, in the that is less than your FL. There is a FL is your cutoff frequency. If frequency is less than FL, there is a limitation of gain. That is a roll off function is there. Once if F is greater than your cutoff frequency, you have a stable gain over the mid-band ranges of frequency, and this part, it is like a high pass filter. It is like a high pass filter. Okay, this is about a low frequency. When you see the higher frequency, you can see that the reactance, the gain is again you have a roll off function. Because of which one? Because of the stay and transistor and load capacitance. These are the three capacitors which will push your gain down. So what you have to understand is the capacitance which is occurring in the higher frequency will be like a connected in parallel with your circuit, whatever you see, like a parasitic capacitance, transistor capacitance, stay capacitance, load capacitance, everything will be in parallel. So it's something like a low pass filter. So that means there is a limitation in the higher frequency and there is no limitation in the lower frequency. That's what you want to understand. So what's happening when it is working in the higher frequency? When happening in the higher frequency, there is a limitation because of the stay and load capacitance. But when you see the coupling and bypass capacitor, those capacitance will be act as a short circuit. It will be act as a short circuit. That is a very interesting. But when it is in the low frequency part, the stay and transistor load capacitance will be act as an open circuit. Only this coupling and bypass will be considered in the model. Okay, but when it is in the mid ranges of frequency, the reactance is, you have a null reactance, because your coupling and bypass capacitance will behave like a short circuit, and the stay and transistor capacitance will behave like a open circuit. Okay, this is what you want to understand. Okay, so what you are going to see now is what is when you consider input coupling capacitor, what is the cutoff frequency formula? That is, I am going to calculate what is the FL. That is a FL formula, 1 divided by tau. So what is a tau? The tau is a rollover. There is a roll off function. That is a product of R into C. So now we want to find what is the product of R into C and what is the FL and what is the gain of when you are considering the input coupling capacitor in your circuit. So another thing you can see, when you short circuit, the impedance will be very less. When you open circuit, impedance will be very large. That is the basic concept of the theory. So with that information, we'll go to the very important part. Okay, so you can see the circuit. Observe the circuit clearly. I have considered the coupling capacitor. In the model also I consider the coupling capacitor because I want to I want to study the input coupling capacitor working property. So I have considered in the model and I am going to derive what is the cutoff frequency for this coupling capacitor effects. Okay, so this is a divider biasing, that R1 R2. This is a DC supply. I am taking output in the collector part. RSI is your source signal resistance, and RE, this resistance will provide the best DC stabilization, right? So that is a feedback element, you can say. This RE is a indirect feedback element. It is connected to the input part, indirectly connected. Okay, so now question is how drawn this to this. Already you have seen many lecture how to draw a small signal equivalent circuit from your given circuit. Okay, so I'll explain here. Okay, so first you can put a emitter, then you can put a base, then you can put a collector. So first part what I suggest you is, first you start with completing a mathematical modeling, that is your transistor part. So that's why I see, so base and emitter and collector, same I have given the name. So now in between base and emitter, what is the resistance? You know, in between a base emitter, you know that you have a resistance R pi, right? In emitter we can see there is a RE resistor is connected, right? So here you have a RE resistor. Then here you know the current gain you will be getting with respect to the looking the emitter terminal, right? So GM times of V pi. GM times of V pi. So this is a mathematical part. So here I am not taking the early effect. Okay, so I am taken the GM times of V pi. That is a current gain factor. Now other than that, you can see here I am removing the VCC. So this R1 and R2 will come parallel. So R1 is coming parallel to R2. Then the capacitance I am considering because I want to study the cutoff frequency formula and other parameters. Then signal resistance, it will be in series RSI, and here you have a inputs AC small signal VA. So this is about the left side. In the right side you can see I am removing the VC, so RC will come to the ground. So you can see, and here is the output, right? So output. So I want to calculate what is the gain. Gain is nothing but a output versus input. Here in terms of voltage, so I can say V0 by VA. That's it. So here thing is they have taken two consideration, that is RIB. This they have taken as a RIB. That is a base resistance. When you look the base part, what is the resistance which is offering with respect to this, including this feedback part, okay, with the including this RE part. So you can see here the IB is coming towards this emitter terminal and IC also is coming towards. So here it's something like a 1 plus beta times of your IB current. That is a reflection rule what we studied earlier, right? Then another thing, another factor I have taken RI. RI is the overall impedance of this amplifier. So I can write RI is nothing but R1 parallel to R2 and parallel to RIB. So what is RIB? That we will derive in the coming slides. Okay, you want to apply KVL and you want to find. Okay, so I hope you are clear how this circuit is drawn in the small signal model. Another important thing you can see in this slide, at the higher frequency, the CC is acting as a short circuit and allowing all signal to the output element, that is through transistor to the output. It is coupled to the transistor to the output. But at low frequency, impedance of XC is become large and there is a limitation in the gain that is introducing as a roll-off function in the response. Okay, this is called as high pass filter. This is called high pass filter. Logic is working here. Okay, now we'll move to the next slide. See, when you see here, I am applying the KVL to find what is a RIB. I want to find what is a RIB. So you apply KVL. So when you apply KVL to this loop, what you'll get, minus 2 plus Vn, then plus 2 minus, you will be getting minus. Okay, so I will be writing here for your understanding, IB R pi plus, entering at a plus, leaving at a minus. So I am taking a leaving symbol for applying the KVL. Okay, so here you know that IB plus IC GM Vp, that is IE is nothing but the sum of your IB plus IC. With that it was written. So into your resistance by Ohm's law it was written equal to 0. So if you take this negative terms to the right side, you will be getting this equation. Right. So another thing, the Vp is nothing but a IB into R pi. Okay, I hope you are clear. Vp is nothing but a IB into R pi. So now if you calculate RIB is this part, right? RIB is this part. So RIB will be V in by IB. So a V in already calculated, and divide this equation by IB. You take this IB outside so that IB will get cancelled. You will be getting R pi plus 1 plus beta times of RE. This is a like a impedance with respect to the base terminal. Okay, so you have to be very clear in that, right? So another important equation here, like a beta change, right? How you know the function, the beta is nothing but a product of GM into R pi. With this assumption only, this beta and R pi they are written as a B, GM R pi they are written as a beta. So with this final equation, RIB equal to R pi plus 1 plus beta RE. So this is the equation you want to remember for the numericals. Here what you are going to see is, we are going to derive the cutoff frequency. We are going to see what is your voltage gain, that is a magnitude which you are interested to do the analysis. Okay, other parameters not required. Okay, so this is your equation for your understanding. I have kept in the slides also. So now you apply like a current voltage analysis you want to do. So here I want to find IA. IA will be your input voltage divided by your what are the elements which is connected in this particular node. You can see RSI is connected, CC is connected, this RI is connected. So I am writing top RSI, CC and RI. So that only they have taken. Okay, you can see here. So RSI, the capacitance in terms of reactance, you know, capacitance in terms of reactance, okay, that is 1 divided by j omega cc. S is nothing but a j omega plus r I, c ri, overall resistance. What is ri? Ri is very simple. How to calculate ri? R1 parallel to R2 parallel to this function RIB. With this you are getting. So RIB already you calculated in the previous slide. From there it was written R pi plus 1 plus beta times of RE. So it was rewritten as RB parallel to RIB. Now I want to find IB here. Okay, so I will remove this. Okay, so now we will see what is a IB. Okay, how you can find IB? You want to use current divider rule. So when you want to find the IB current, you want to look the opposite path, that is your opposite terminal. So that is your source current will be II. So I am writing here Ia into opposite resistance is Rb divided by Rb plus Rab. That's all. Very simple. So it was written here. You know that already you have explained you V pi is nothing but a Ib into R pi. They have taken. Okay. So we know the output voltage. It is you have explained in the many slides. So V naught equal to I into R. Okay. So when you find the output resistance, you want to short circuit this VA. So V pi will become 0. So GM V pi also will become 0. So you have a resistance RC only. Okay, you have output resistance RC alone. Okay, what is the current here? The current will be GM times of V pi. So with that I can write GM V pi RC. We know that your output current IC and output current like a load current will be opposite. With this, considering this assumption, I am taking minus here, so that it was written like a minus GM V pi into RC. I hope it is clear. This moving with this continuation we are moving. So we have discussed up to this, right? We have to discussed here up to here. GM V pi RC. Already we know V pi is nothing but a IB R pi. So with that it was written GM RC IB into R pi. IB you know already, you have defined. What is IB? IB is here RB divided by RB plus RIB into IA. So I want to plug in here. Okay, I have plugged in here. So once you substitute IB, so you will be getting minus GM R pi into RC into RB divided by RB plus RIB into IA. I hope it is clear. Now I am substituting IA equation also. In the previous slide you can see IA equation. Okay, so this is your IA equation. So IA equation also I am substituting. If you substitute, you will be getting this part, right? You will be getting this VA divided by RSI plus 1 divided by SCC plus RI. So I hope it is clear. Now we will go to the final part. Okay, see now this is your equation. So this is your what is my expectation is I want to find a voltage gain. Okay, I want to find a voltage gain. So V naught by VA. So you have a V naught. You divide this equation by VA. Okay, if you divide this by VA will get cancelled. You can find your voltage gain. Then you want to take LCM. If you take LCM, this reactance will come top. With that, your final equation will get. So that's it. Okay, so you can see what I said. It was done here. Okay, so they have taken LCM. Then they have divided that previous equation by VA. So they have divided this previous equation by VA. So you get this equation. Okay, so in terms of transfer function, it was written. Already I said we are interested to see only the magnitude and cutoff frequency. Why you are calculating the transfer function is to calculate your tau s. Okay, if you know tau s only, you can find what is the cutoff frequency. Now what I am going to do is, see, I am going to multiply and divide by the value this RSI plus RI. If you divide and multiply, okay, so they have multiplied here. Okay, so they have multiplied here RSI plus RI into CC. You will be getting like this. So this whole value I am writing as a tau s. So I am repeating again. In this equation they have multiplied RSI plus RI. Okay, they have divided and multiplied. Okay, so RSI plus RI. This whole value as a tau. This is a transient. This is a time period. Okay, so this is a important part here. So this is a time constant. You can see here this is a tau s. S defines the capacitors connected in the series, right? So tau s equal to RSI plus RI into CC. So this is a tau part, time constant part. With that, we can calculate your cutoff frequency 1 divided by 2 pi tau s. So if you substitute the tau s, you will be getting this final equation. So your magnitude part is this part, right? The magnitude part is this part. This is your magnitude part. This is your magnitude part. This is the magnitude part. If you want to take a in terms of dB, you can write like a, I can write like a 20 log of this whole value. This is what they have written here. Okay, so what you are interested is, you are interested to find your cutoff frequency, and we want to see the magnitude, and we can plot in dB also. Okay, so like so this is your response, right? This is your response of your input coupling capacitor. You want to know what is a FL, you know the formula for this, and what is the gain you want to calculate, that can be get from this formula. So this is your input coupling capacitance derivation part. I hope it is clear. Okay, so this is a problem which is relevant to the considering the input coupling capacitor. So what is the best thing is, you want to separate this problem into three parts. Okay, so no need to draw the small signal analysis, like this is only for understanding. Okay, suppose in exam if they are asking to put the hybrid model, you can put. Okay, so you'll be getting the corresponding marks. So if they're not like they are not asking, there is no question problem statement like drawing the hybrid model, no need to draw. You can draw only for your understanding. So first part is you want to do the DC analysis. In the DC analysis, what you want to find is, you want to find, it is the same for most of the problem. You want to find VTH, you want to find RB, and you want to find IB, and you want to find IC. These are the DC point. After fixing the DC point, you want to find a small signal analysis parameter, that is R pi, GM, and VA. Here VA is not given. Okay, VA is given as infinity, so I am not calculating. So for this problem, what are the values they have taken? R1 they have taken as a 51.2. okay, 51.2 kilo ohm. R2 they are taken as a 9.6 kilo ohm. Beta 100. Okay, what is RC? RC will be 2 kilo ohm. Okay, RC will be 2 kilo ohm. Okay, so I given this value, with this we will proceed. Okay, so first we will be finding the VTH. You know, already I explained you how you got this VTH. So VTH formula will be VCC into R2 divided by R1 plus R2. So this is a point where you are finding your VTH, that is a VB. So it is something like this, right? We have explained. I explained you. I am not again going to teach you. So this is the part you are calculating, that is R2 divided by R1 plus R2. It was supplying. So you will be getting your VTH 1.6 and RB. So that is a equivalent resistance. So R1 into R2 divided by R1 plus R2. So 51.2 into 9.6 divided by 51.2 plus 9.6, you will be getting 8.08 kilo ohms. I want to find IB also. So what is the formula? While you are applying the KVL in the input side for the Thevenin sequence circuit, you will be getting this formula. So VTH minus VB divided by RB plus 1 plus beta times of RB. Plug in all values. So here the VB is 0.7. It is a fixed value. You take a silicon. So you can use same for all the problems, right? So if it is silicon, so beta is 100. So 100 plus 1, 101. RE is 0.4 kilo ohm. So here you can write RE is 0.4 kilo ohm. Okay, so you will be getting 1.829 10 to the power minus 5 amps. Okay, now IC I want to calculate, that is IC is the beta times of IB. You will be getting 1.81 milliamps. Then with that DC part is over. Then from here I want to find your AC small signal parameters. Small signal parameter, that is GM formula is IC by VT. IC already calculated 1.81 divided by Vt. Vt is the thermal voltage 0.026. You will be getting 69 milliamps per volt. Similarly, R pi I have to calculate, that is thermal voltage beta divided by ICQ. Vt is 0.026, beta is 100, so ICQ already defined, so you will be getting 1.4 kilo ohms. With that, your your small signal parameter is over. Va is not, it is infinity is given, so R naught is also infinity. With that, your small signal parameter over. Now we want to calculate your tau. Okay, we want to calculate tau. Okay, so how we will calculate? What is the formula for tau? RSI plus RI into CC. What is the RI formula? RI formula already we have studied. We have studied, right? So I'll show you in the previous slide we have discussed, right? So RI is nothing but a R1 parallel to R2 and R2 parallel to RIB. So this you want to look from this left side. You can find this RI part. Okay. So with the same equation we written here. So Ri equal to R1 parallel to R2 and parallel to RIB. What is RIB? RIB is nothing but R pi plus 1 plus beta times of Re. Okay, so I have substituted R1 51.2 and R2 9.6, R pi 1.44, 1 plus beta 101, Re 0.4, and you will be getting 6.77 kilo ohm. So your work is, you want to take the calculator and check whether you are getting this 6.77. Okay, so that is your work. So if you are not getting, you want to see where you are making the mistake and try to get the answer. Okay, then I want to calculate tau s. So already you know what is RSI. It is given the problem, that is 0.1 kilo ohm. Ri calculated 6.77 kilo ohm, and C is, there is a coupling capacitor 6.87. So if you substitute, it is a very simple. Just addition and multiplication will be getting 6.87 milliseconds. So substitute and try to calculate your cutoff frequency. Here what you have determined here is, so this is a cutoff frequency which you have calculated. What is FL? That is 23.2 Hertz. Now I want to find what is the gain. That is the next part. So I have substituted 1 divided by 2 pi tau s, which we calculated, that is 1 divided by 2 pi into 6.87 milliseconds, you will be getting 23.2 Hertz. Now we are going to find what is the maximum gain. Okay, so what is the formula for gain? Gm R pi into RC divided by RSI plus RI into RB divided by RB plus RIB. So already you know most of the values, just you want to plug in and you want to find the answer. What is RIB? RIB is nothing but because see, here you have calculated like a overall. I don't know what is RIB separate, so I am trying to calculate separately because I want to substitute here, that's why. So Ri plus 1 plus beta Re, so that is R pi is 1.44 and beta is 100 plus 101, and Re is 0.4 kilo ohms. See, make sure that all are in the same MKS unit. If you are doing in the kilo ohms, everything in the kilo ohms. If you are doing the ohms, everything should be in ohms. So that is giving a correct answer. So you have to be more precise in that. So RIB will be 41.8 kilo ohm. Okay. Now you know all the values. You know what is the GM. You know what is the R pi. You know what is the RC. You know what is the RSI. You know what is the RI. You know what is the RB. You know what is the RB. You know RIB. So if you substitute, you should get the 4.72. Okay, so you should get this 4.72. I hope you will get this answer. Try to put in the calculator and try to get the same answer. Okay, so already said, so coupling capacitor is produce a high pass network, right? So that's what we studied in the earlier slides. So this is some practice problem you can try. This is a problem from Neamen book. You can try it. So answer also is given down, so you can cross check your values. Thank you.